talk about relation between Kp and Kc from the chapter equilibrium. Relation between Kp and Kc. Students, we know Kp is the equilibrium constant in terms of partial pressures, whereas the Kc is equilibrium constant in terms of active masses. Let us consider a hypothetical reaction which is in equilibrium. AA plus BB. Assume all the gases are present in the reaction, involved in the reaction. AA gas plus BB gas, which is in equilibrium with CC gas plus DD gas. DD gas. Expression for Kp, equilibrium constant in terms of partial pressures, we can write it as Kp is equal to pressure of C, capital C, to the power C, pressure of D to the power D, divided by pressure of A to the power A, multiplied by pressure of B to the power B. We can write like this, right? So Kp is equilibrium constant in terms of partial pressures. Product of partial pressures of the products raised to the power of their stoichiometric coefficients divided by product of partial pressure of the reactants raised to the power of their stoichiometric coefficients. Kc we can write it as active mass of the C to the power C, active mass of the D raised to the power of D, divided by active mass of A to the power A and active mass of the B to the power B, we can write. C included in the square bracket indicates that is a active mass. Active mass is concentration in moles per liter. Molarity, active mass is molarity. Students, from the ideal gas equation we can write PV is equal to nRT. Ideal gas equation PV is equal to nRT. If you transfer V to the other side of equation, we will get N by V into RT. P is equal to N by V into RT. Here N by V is the same as the active mass. Number of moles divided by volume will give us molarity. For a gas A, we can write Pa is equal to active mass of A multiplied by RT. Similarly, for the gas B, we can write Pp is equal to active mass of B multiplied by RT. For C, we can write Pc is equal to active mass of C multiplied by RT, and Pd is equal to active mass of D multiplied by RT, right? So now we will take this equation. Kp is equal to partial pressure of C to the power of C, partial pressure of D to the power of D, divided by partial pressure of A to the power A, partial pressure of B raised to the power of B. Like that we can write. Then in place of Pc, we can write it as active mass of C multiplied by RT, right? So which is Kp is equal to Pc, we can write it as active mass of C into RT whole power C. Similarly, Pd we can write it as active mass of the D multiplied by RT whole power D, divided by Pa we can write it as active mass of A into RT whole power A multiplied by active mass of B multiplied by RT whole power B, we can write. Right? Let us separate the concentration terms and RT terms. So concentration terms I will write separately, that this is in the form of AB whole power M we can write it as A power m multiplied by B power m. Here C into RT whole power C, we can write it as C power C into RT power C. We will write that RT term separately. So from this we can write D power D by this is A power A multiplied by B power B, we can write. So what is the remaining terms? When we expand this by using the formula AB whole power m, we will get A power m, B power m. C power C already we wrote. Remaining term from this is RT whole power C multiplied by this C is a small c, RT whole power D divided by RT whole power A multiplied by RT whole power B. Then Kp is equal to this total term, this total expression, we can write it as a Kc. This I am writing it as Kc multiplied by this is RT power C, RT power D, RT power A, RT power B is there. This we can write it as RT whole power C plus D, C plus D. When the bases are same, powers can be added. These terms also added. When this will comes in the numerator, this will becomes as minus A minus B. So total term on simplification we can write it as Kc into RT power C plus D minus A plus B, minus of A plus B. So Kp is equal to Kc into RT power, this we can write it as a delta Ng, where delta Ng indicates the total number of gaseous products moles minus total number of gaseous reactants mole, right? For example, if you take a reaction 2HI gives rise to H2 gas plus I2 gas. All the gases are involved in this reaction. Then delta Ng for this reaction is equal to total gases moles of the products is 1 plus 1, it is 2, minus number of moles of gases reactants is 2. So we are getting delta Ng is equal to 0. Next let us see the conditions. Kp is equal to Kc into RT power delta Ng. RT power delta Ng. First condition, if delta Ng greater than 0, that is delta Ng value is a positive, then Kp is greater than Kc. Second condition is if delta Ng is less than 0, if the delta Ng value is negative, then Kp is less than Kc. Third condition, Kp is equal to Kc. For this there is two conditions can be applied. First one is if delta Ng is equal to 0, delta Ng is equal to 0, the relation between Kp and Kc is Kp is equal to Kc into RT power delta Ng. RT power delta Ng. When we substitute delta Ng is equal to 0, Kp is equal to Kc into RT power 0. Anything to the power 0 is 1. So Kp is equal to Kc. For Kp is equal to Kc, there is two conditions. First condition is if delta Ng is equal to 0, then Kp is equal to Kc. Then the second condition is if the product of R and T that is equal to 1, then also Kp is equal to Kc, because 1 to the power anything which is equal to 1. So that is whatever the value of delta Ng, if the RT is equal to 1, then Kp is equal to Kc. Let us find out the temperature at which Kp is equal to Kc, whatever the delta Ng value. So substitute R value as 0.0821 into T is equal to 1. So T is equal to 1 divided by 0.0821. On simplifying this, we will get it as 12.18 Kelvin. At 12.18 Kelvin, Kp is equal to Kc, whatever the value of delta Ng. Thanks for watching.